Now we can going to a typical objective function formulation. Now for any physical system, the objective function formulation follows this principle only. So once if you understand this, you can implement this, or you can implement this to any system that can be modeled in this way. So let's say we normally use an Euler's forward integration for the discretization of the system and try to predict the future value. So let's say in the equation 1, if you see, the dx by dt is taken as x of k plus 1 minus x of k by ts. So you are actually at the present sample t is equal to k, you are trying to get the future sample. So by using the Euler's forward discretization with the system model, you can actually predict or get an estimate on the future value of a particular value of a particular parameter x. And a general objective function formulation is given by the equation 2. If you closely observe equation 2, the first term is the reference value, the second term is the predicted value. So the predicted value using the equation 1 for nth control action. Let's say the converter might have 0 to n control actions. So for the nth control action, what is the predicted value? You are just trying to take into the objective function. So this typically the objective function Jn is defined as the equation 2 that is appearing on the screen. So if you just see, it is just difference between the reference value and the actual value or the predicted value. So you are trying to have an error between the predicted value and the reference value and trying to formulate an objective. So the objective here is to minimize the error, which is very intuitive. So usually for any control system, if I have a reference, I would expect the actual value to follow the reference. So my objective is to minimize the error between the reference value as well as the predicted value. That is what the objective function, the generalized objective function that we normally see in any control, any model predictive control implementation. So here, if you see the x, the value x can take any of the system variables, like it can be torque, it can be current, it can be flux, it can be speed, etc., etc. And h is called as the prediction horizon, that it gives an idea on how many samples that we are going to predict, or how many samples that we are going to predict the future in future. Now, as I have shown here, the objective function need not have a single term. It can have multiple terms. It can have torque plus current plus flux, or speed plus flux, or speed plus current. So it can have multiple control objectives embedded into the same function. And the optimum control action is obtained by minimization of jn for all the n control action. So whichever control action gives you the minimum value of this objective function is taken as the optimum control. It is in a sense, it is like you have n number of control actions and you need to pick one. The one that gives the minimum error is picked. So that is what typically is done. Now the lambda that is being put in the first before the expression is typically called as the weighing factor, which gives a relative importance of the function that you are actually considering. And the design of this is not pretty straightforward, which is heuristic in nature. People have implemented, or people have experimented it and have reported the use of the values. Typically a range of values can be found in the literature, but there is no clear-cut method that is available in the literature for the design of the weighing factor. So this is what the overall a block diagram of a model predictive control is seen. So the x can be is any state variable of the plant. For motor drives, typically x is considered to be current, torque, flux, and voltage. For grid connected systems, the states can be voltage, current, and power. Now, in order to compensate for the delay that is occurred in computations, a two-step ahead predictions are typically used. So the prediction horizon is taken as 2 in practical implementation. Now coming to the advantages of the finite control set and disadvantages of the finite control set. As we can see, PWM modulators are not used, so the control is pretty simple and faster. They have fast dynamics as the output is a direct control state. So the output is a direct control action which is directly implemented on the converter. And the PI controllers are not used. Then the cost functions are flexible. Now, this is the what I have mentioned earlier, that the cost function is flexible. You can have n number of entries into the cost function, and you can include any number of constraints on the system parameters, provided they can be modeled appropriately. Now, if there are any errors in the modeling, they can also be considered to some extent, but this is again subjective thing, which may can or which may help in formulation. And many a times an accurate model is definitely needed. Small deviations here and there are fine, but an accurate model is needed. Some modeling errors can also be included. Then some methods in the reported in the literature also consider the time delay that is caused in performing the calculations, and they have mentioned, or they have reported that a two-step ahead prediction will be helpful. Now, coming to the disadvantages, yes, if you have n control actions, you need to perform n calculations, so you need a fast processor to perform, as I have already mentioned. Then they are this control methodology is mainly characterized with variable switching frequency. So whenever there are a pure sinusoidal outputs are required, it is very difficult to design and control or design the filter circuits when you have a variable switching frequency. Of course, many modifications of the conventional model predictive control methods are now available, which can work on constant switching frequency as well. However, one noticeable difference when compared to the conventional methods, the model predictive control methods have, is the stability of the system. Understanding the stability of the system or formulating the stability of the system is not straightforward, as they are mainly defined in time domain rather than the frequency domain. It is very difficult to understand the stability of the system, unlike the PI controllers. And again, yeah, accurate model of the system is always necessary. Now, having spoken much more many things about model predictive control, its advantages, its types, and other things, we'll see how, by taking a small example, we'll see how an implementation of model predictive control can be done. Now let us take an example of a three-phase inverter, a six-switch inverter feeding an RL circuit, RL load typically. Now, as you might have seen, this is a conventional three-phase inverter with six switches, and the each pole of the switch, A, B, C pole of the converter, can be clamped to the positive DC rail or negative DC rail with an appropriate control action given to the particular leg of the converter. And the main constraint in this control is no two switches in the same leg are operated or turned on at the same instant. So if the top switch is on, the bottom switch is off, and if the bottom switch is on, the top switch is off. So typically the bottom switches are operating in complementary fashion with the top switches. So a switching state or a switching action for a particular pole of a converter can be defined as the table that is shown below. So whenever the switching state is 1, the output pole voltage V, A, and O, the voltage between the phase and the midpoint of the DC link, is 0.5 VDC. Whereas whenever the top switch is turned off, that means the bottom switch is turned on and the point A is clamped to the negative DC bus, and the pole voltage typically is minus 0.5 VDC. Now, because there are three legs, and each leg at a given point of time, each leg can have either top switch turned on or bottom switch turned on. So with this kind, we have in total there are 8 different switching possibilities, or 8 different switching states rather they are called, so which can be shown here below. So starting from 100, 110, 010, 011, 001, 101, 111, and 000, these are the 8 possible switching states for this converter. So at any given point of time, the converter will be operating in one of these 8 particular switching combinations. That is what this means. Now, a space vector generated by this converter is given by this formula, which is Vs is 2/3 of VAO plus VBO e power minus j 2 pi by 3 plus VCO e power minus j 4 pi by 3, and which is again when converted to alpha beta can also be considered as V alpha plus JV beta. Now substituting these values for all the switching states, will end up for voltage state V1, the vector lies on the x-axis or on the alpha axis, whereas for voltage vector V2, the vector lies 60° to it, and they lie on the vertices of a regular hexagon with the size 0.2 by 3 VDC. So these are the available switching combinations, which are the control actions that are available for this converter. So rather, we can also see them as the control actions on this inverter, because at any given point of time, the converter can only operate in one of these switching states. That's the point here. Now, so yeah, if you can see, there are 7 distinct space vector locations, 6 active vectors, like with 6 non-zero vectors and 1 zero vector. That is how they are termed in literature. And then the current, typically the current flowing through the load, I can be given in the formula per phase in per phase notation, can be given as V minus RA by L. And it can also be, this equation can also be considered in vectorial form as well. Now, converting using Clark's transformation, converting the 3-phase quantities into 2-phase quantities with the sign convention that I have already mentioned, we can, and discretizing this equation, the equation 4 that we have seen here, we'll get the future current I of k plus 1 as equation 5. Now, it is important to see the equation 5, that for a given voltage state V of k, and for a given measured current I of k, you are in a position, if you know the plant parameters R and L, and for a given sampling time, you can predict what is I of k plus 1. So here you can see, for each value of V of k, you are in a position to tell what is I of k plus 1. This is the major or the important point that one needs to understand. So it is like, if I have a current at this instant, if I know the current at this instant from the plant, if I know the voltage that I'm, or voltage vector that I'm going to apply, or the control action that are going to apply, what is the, how the current is going to change. So for every physically possible control action, you have a predicted value, which you can really mathematically sort out or mathematically find out from the plant model. So this is one, this is the main motivation beyond prominence, or this is the main key feature of this finite control set model predictive control to be so prominent in the recent times. So you can actually understand how the system behaves for each and every control action that you have. So that enables me to formulate a better control perspective. So each and every control action at my disposal, I know how the system behaves. So I can beforehand I can find out what is the control action that is optimum, or that is needed to, in order to control the system on in a specific direction, or in a specific way that is needed. That is what is the control philosophy that this model predictive control actually says. So a typical objective function is a similar error minimization can be taken in alpha axis and the beta axis, the alpha component and beta component. So in this case, we have taken 3 balanced currents. So we have given equal weightage to the alpha current and beta current, which is typically how normally we do. And the optimum switching state is obtained. So this value of objective function in the equation 6 is evaluated for all the 8 possible switching states that are available for the converter, and the state that gives the minimum value of the objective function is taken as the optimum switching state and is fed to the converter in the next sample. So in a way, it is like you are trying to minimize the error for every given, or find out the error for every possible switching state of the converter, and you are trying to minimize that error, and you keep on doing it at a particular sampling rate TS. So here the advantage in the control, or the advantage uh, or the parameter that actually controls the switching, is the sampling time. And the philosophy or the algorithm, what is actually true, it tries to track the reference in all the samples. In every sample, rather, it would try to just track a reference, like it would try to minimize the error always from the reference quantity to the actual predicted quantity. So the main features, or the main important points to be considered is, from the implementation that we have seen, the formulation of the objective function is simple. It's just a simple error minimization in the alpha axis and the beta axis. Now, if you have different control parameters or different control objectives, let's say if we have seen an example where we have both the currents to be controlled, which are of having the same dimension. What if the control objectives have different dimensions? Whether how it can be done, can it be done, or is there any issue? So that is one another important parameter that model predictive control offers, or the important advantage that model predictive control offers is, it doesn't matter for me what is the dimension of the control parameter that I'm planning to put in the objective function. It doesn't matter what range of values it takes. Let's say if I what range of values it take normally, and the basic objective function is modified and for control of various parameters and various objectives, to meet various objectives in the literature. Now we can see these are some of the examples of the objective functions that are used for controlling various variables or parameters that are available in the literature. Now we have seen a three-phase balanced currents. Some time ago I have said that the currents are three-phase balanced, so there cannot be a zero sequence current. What if there is a zero sequence current that is flowing? Now you want to control it. You can simply add that with an appropriate weight to the objective function, and you just modify the objective function. After all, the zero sequence current can be measured as sum of the three currents, IA plus IB plus IC, that anyway you are measuring. So you can actually get the measure the value of zero sequence current for a given control action. You can also measure the zero sequence current in the future and then try to control it by implementing it. And another control objective function that is normally predominantly seen in an induction machine is torque and flux control, wherein the torque error and and the flux error are controlled together. This is by far the most widely used predictive control method in control of induction machine. And you can see here, this kind of an objective function, the torque error plus lambda into flux error, is being put to use in control of induction motor. Now, the torque error is on having a dimensions of Newton meters on a different range of values. Like typically the torque goes in the number of like some tens of Newton meters or 20 30 Newton meters, whereas the flux typically is less than 1.5 webers for any induction machine. So this objective function can take wide range of parameters which can have different range of values. And then for a control of common mode voltage, an equation like given in 9 can be put to use. Then for switching losses, let's say your converter have a switching redundancies, like the same vector can be obtained by using two different switching combinations. Even then you can have a constraint, or you can have a modification in the objective function. Depending on the present state, you can find out which state gives lesser switching commutations. You can put that state into, or you can switch that state instead of switching another state that is having higher switching commutations, thereby minimizing the switching losses. So these are some of the modifications that are available in the literature. There are many more, and you can explore by referring the literature. So having said that, we'll just see an implementation of two most popular methods for induction motor control and wind up this session. So the main most popular control methods for induction machine are predictive current control and predictive torque control. Predictive current control, the philosophy is more on the field oriented control principle, whereas the predictive torque control, the philosophy is more on the algorithm is more based on the direct torque control approach. So we'll typically see how the predictive torque current control is implemented first, then we'll go to predictive torque control and see what are the differences in implementation wise in both the predictive current control and torque control. Now looking at the predictive current control, the stator equation or stator current equation in complex form in an induction motor is given by this, the equation 11. I'm not going the derivation of this, or I mean, don't be scared with the equation or the big equation that you look at onto the screen. It is available in the literature. You can just go through the derivation of this, but it is a complex equation. The whole point I wanted to show is the equation looks so complex like this. Now, after discretization, the equation becomes something that is shown in the equation 12. So you have a predicted current for a given stator voltage Vs, or the voltage that is applied to the machine Vs. And again, the usually in induction machine control, if you see the field oriented control principle, the torque and flux are typically controlled with two reference currents. So the control is happening in a reference frame which is oriented with one of the fluxes, and the most simple field oriented control is the rotor field orientation. So typically in a rotor field oriented control, the reference currents that are generated are when the machine is operating. Of course, when the machine is operating under base speed of operation, the id star and iq star, the reference currents in the d axis and the q axis, wherein the d axis is oriented to the rotor field or the rotor flux psi r, can be obtained through this. That is, id star is the psi r by lm, and iq star is obtained from the torque. So thereby inherently there is a decoupling, wherein the d axis component of the current controls the flux, whereas the q axis component of the flux controls the torque. Now these two references are converted back to alpha beta frame, and a typical objective function that we have already seen in the converter current control a while ago is implemented in finding out the switching action or control, the switching state of the converter, and the switching state is given directly onto the converter. So the block diagram looks something like this. So you are measuring the motor currents, you are estimating the rotor flux, and then you are doing a prediction of the current. I alpha of k plus 1 and I beta of k plus 1 are obtained, and there is a speed reference, and the speed reference, a PI controller is typically employed here to get the torque reference, and from the torque reference and the flux reference, typically the flux reference is kept its rated value. So the flux reference and from the torque reference, you will get the two currents, id star and iq star, and they are converted to alpha beta, and they form the reference currents I alpha, I beta, I alpha star and I beta star, and they are now compared with a cost function, and then the gate pulses or the switching state of the converter is directly obtained and given to the converter. This is how the predictive current control can be implemented. Wherein coming to predictive torque control, it mainly depends on the principle of direct torque control, wherein the torque and flux are directly controlled. So the torque and flux are directly controlled in this scheme, whereas how it can be done is the flux can be predicted using the equation that is shown in 15. So the psi s of k plus 1 is taken as the present flux psi s of k plus sampling time into vs of k minus rs is of k. So this is basically the simple back EMF estimation of the flux. Now the torque from the estimated flux, the torque can be computed from the equation that is given in 16, wherein from the product of psi alpha I beta minus psi beta I alpha. Now a typical objective function can be formulated. This we have already seen. Uh, And the weighing factor, for this weighing factor, in the literature it is mentioned that the nominal torque to the nominal flux, the ratio of nominal torque to the nominal flux is a good starting point, even though there are many more in some papers in the literature mention some around 10 times this value as a very good starting value. But as a good starting point, you can just normalize these equations, I mean these errors into single value by using this objective function. So by employing this lambda equal to t nominal by psi nominal, you can just get these two values into the same range. So typically this is one good starting point. However, in certain literatures they have mentioned that a value as high as 10 times this value can give better performance. So the block diagram for this predictive torque control is like this, where you have a speed control. The speed pi output gives you the torque reference, and you have the stator flux reference. And from the machine currents and the machine speed, you will be estimating the flux and the torque. And once you get the torque estimation and the flux estimation, you implement the objective function and arrive at the converter switching state directly, which can be imposed on the converter. So this is how the predictive torque control algorithm works. Now, to have a close comparison of predictive current control and predictive torque control, we can see PTC is much simpler owing to its lesser computations, whereas PCC has the ABC to DQ transformation. So it is little more complex to implement. Whereas the number of computations in PCC are much lesser because you stop with the current prediction. Hence, PCC can go for a higher sampling when compared to PTC. And the tuning of weighing factor in PTC is very critical and very difficult, as it directly affects the performance of the system, whereas there is no weighing factor in PCC. So because it being a direct torque control method, the torque ripple is much lesser in PTC when compared to PCC. However, the PTC method is robust in over variation of LM, as the estimations of the values doesn't involve the value of LM. However, the estimation of flux is directly dependent on the stator resistance, and hence PTC is little sensitive to variation in the stator resistance, whereas PCC is much more robust to variation in stator resistance, but it is sensitive to over variation of LM as it predicts the stator currents. And concluding the webinar, so what we have seen today is we have seen what are the power electronic converters and what are the conventional control methods and their attributes, mainly the attributes of the conventional control methods, how the conventional control methods really are implemented, and how different is model predictive control in handling the multiple input and multiple output systems and constraints, and the types of continuous control set predictive control and finite control set predictive control, and understanding the implementation of PCC and PTC and PCC methods. So with this, I'll wind up the session, and these are some references, some selective references that I have referred.